All right, so get this, that classic physics experiment where you shine a light through two tiny slits.
Yeah.
Turns out, even if you shoot single particles of light, one by one, they create an interference pattern on the screen behind the slits, like they're somehow going through both slits at the same time.
Right.
That's the kind of mind-bending stuff we're diving into today, the world of quantum mechanics.
Yeah. It really is one of the most fundamental experiments in all of physics because it just shows how all of our classical intuition about the world completely breaks down at the quantum level.
It's wild. So for this deep dive, we're going to be unpacking this awesome article called The Illusion of a Single Path. I was reading it and I was thinking, wait, does this mean everything is just a blur of possibilities until we look at it?
Well, you're not far off. Quantum mechanics really does shake up our understanding of reality. Imagine a lifeguard, running to rescue a swimmer. They don't just run straight into the water. They kind of angle their path to get there the fastest, even though it might seem longer.
Okay, so they're optimizing for time, not distance. But what does that have to do with quantum mechanics?
Well, it illustrates a key principle called Fermat's principle: light takes the path of least time.
Okay.
Now, think about how light knows to do that. It seems like it should calculate all the possible paths and then choose the fastest one, right?
Yeah, that's what my brain wants to say. But doesn't that mean light has some kind of consciousness?
Not quite. The amazing thing is that light doesn't choose at all. According to quantum mechanics, it explores all possible paths simultaneously.
Hold up. That's like saying my car is driving to work on every single street in the city at the same time.
It's wild, isn't it? It challenges everything we think we know about how things move. And it's not just light. All matter, including the stuff that makes up you, has these wave-like properties.
Okay, you're losing me a little here. I thought waves are like ocean waves, not solid objects.
It's a tricky concept, but picture it this way. Imagine a particle not as a tiny ball, but as a wave packet. It's spread out, existing in multiple places at once.
So are you saying everything is just a fuzzy blur until someone looks at it? Like, does my coffee mug only become solid when I'm looking at it?
Well, that's where the idea of superposition comes in. A particle can exist in multiple states at once, like passing through both slits in that experiment. But when we observe it, it collapses into a single definite state.
It's so bizarre. So the act of observation somehow forces the particle to choose a reality.
In a way, yes. The observer plays a crucial role in quantum mechanics. It's like the universe is saying, hey, I've got all these possibilities laid out, and you get to choose which one becomes real.
Wow. I'm going to need a moment to wrap my head around that. So how did scientists even come to these crazy conclusions?
Well, it all started with some problems in classical physics. You know how things get brighter and hotter the more you heat them up?
Yeah.
Well, scientists in the late 1800s were trying to figure out exactly how that worked.
So like, why does a glowing ember emit different colors of light as it heats up?
Exactly. The problem was their calculations based on classical physics predicted that objects should emit an infinite amount of energy at high frequencies, which obviously doesn't happen. They called it the ultraviolet catastrophe.
Sounds dramatic. So what was the solution? Did they just ignore the math?
Actually, a physicist named Max Planck came up with a revolutionary idea. He proposed that energy isn't a continuous flow. It comes in tiny discrete packets called quanta.
So it's like saying instead of a smooth ramp of energy, it's more like a staircase with distinct steps.
That's a great analogy, and this radical idea actually solved the ultraviolet catastrophe. It was a huge turning point in physics, laying the foundation for quantum mechanics.
And then Einstein came along and ran with that idea, right?
You got it. He applied Planck's idea of quantized energy to light itself, suggesting that light is made up of these tiny packets of energy called photons. This explained the photoelectric effect, where shining light on a metal can knock electrons off, but only if the light is above a certain frequency.
So it's like light is made of these tiny energy bullets, and if they're not powerful enough, they can't dislodge the electrons.
Exactly. This was another huge leap forward, solidifying the idea that energy is quantized. It comes in these fundamental units that can't be divided. And this concept was crucial for understanding how atoms work, too.
Right. I remember learning about Niels Bohr's model of the atom with electrons orbiting the nucleus.
Yeah.
But I always thought those orbits were kind of arbitrary, like why those specific distances?
That's where it gets really cool. Bohr proposed that electrons could only occupy specific quantized energy levels. Their angular momentum was also quantized, which basically means they could only spin at certain speeds.
So those orbits weren't random at all. They were determined by these fundamental quantum rules.
Precisely. And what's even more amazing is that Bohr's model, based on these quantum ideas, perfectly predicted the colors of light emitted by hydrogen atoms.
Wow, so these seemingly arbitrary rules actually explain something real and measurable about the world.
Hmm.
But how did they explain why those rules existed in the first place?
Well, that's where things get even more mind-bending. Remember how we were talking about light acting like both a wave and a particle?
Yeah.
A physicist named Louis de Broglie proposed that all matter, not just light, has wave-like properties. He even came up with an equation connecting a particle's wavelength to its momentum.
Wait, are you saying that everything around us, this table, my coffee cup, even you and me are actually
Oh,
waves?
in a way, yes. This was a revolutionary concept.
Okay.
It suggested that matter wasn't just a bunch of tiny particles bouncing around. It had a wave-like nature that affected its behavior.
Okay, my head is officially spinning. So
Yeah.
light acts like a wave, and a particle matter acts like a wave and a particle. What does this all mean for how things actually move?
That brings us back to one of the most famous experiments in physics, the double-slit experiment.
All right, let's dive into that. But first, can I just say, this whole quantum mechanics thing is blowing my mind. Okay, so back to this double slit experiment. It sounds pretty simple, but it's got these insane implications for reality, right?
Yeah, that's right. The double-slit experiment really is like the cornerstone of quantum mechanics. It just really drives home how different the quantum world is from what we see every day, in our classical world.
So walk me through it. What happens exactly?
So imagine you have a barrier with two tiny slits cut into it, and behind that barrier, there's a screen that detects, where particles hit. Now, if you shine a beam of light at the slits, what would you expect to see on the screen?
I guess two bright spots, one for each slit, right? Seems pretty straightforward.
Exactly. That's what you'd think if light acted only like a wave. But here's where things get weird. When you start shooting individual particles like electrons at the slits, one at a time.
Okay, so now it should be like tiny bullets going through one slit or the other, hitting the screen behind in two distinct spots.
That's the logical conclusion, but that's not what happens. Instead of two spots, you get an interference pattern, multiple bright and dark bands across the screen.
Hold on, that's like each electron is going through both slits at the same time and interfering with itself. How is that even possible?
Yeah, that's the million-dollar question. The double-slit experiment shows that each electron isn't choosing a single path. It's actually going through both slits simultaneously like a wave, even though it's a single particle.
So it's like each electron is spreading out and becoming a wave, then somehow collapsing back into a particle when it hits the screen.
You're getting the idea. Until it's measured, the electron exists in a superposition of states, meaning it's in both states at the same time. And when we observe it, that wave function collapses, and we see it as a particle in a single location.
This is bending my brain a little bit. So the
Yeah.
electron is kind of like a cloud of possibilities, and the act of observing it forces it to choose a specific point to land on.
That's a great way to think about it.
Yeah.
It really challenges our classical notion that things exist in definite states before we observe them. It's more like they exist in a fuzzy state of potential until we look at them.
It's kind of a freaky concept. If
Right.
we're not looking, does that mean things aren't really there?
It's not that things aren't real until we look at them. It's more that their reality is described by probabilities rather than certainties.
Okay, so it's like a dice roll. The possibilities are always there, but the actual outcome isn't determined until you roll it.
That's a good analogy.
Yeah.
It's not that the electron isn't real until we look at it. It's that its location, its path, is described by probabilities.
Okay, so this is all happening at the subatomic level.
Yeah.
Does this fuzzy probabilistic reality apply to bigger objects too?
Yeah.
Like, is my dog actually a wave until I look at him?
Well, technically, yes. But the larger the object, the less noticeable these quantum effects become. For everyday objects, the probabilities converge so closely that they essentially behave like the solid, predictable objects we perceive them to be.
So it's not like I'm going to walk through a wall because of quantum tunneling or anything.
Probably not, though on a small enough scale, particles can actually tunnel through barriers that they classically shouldn't be able to pass.
Wow, this is seriously stretching my understanding of reality. So the double slit experiment basically proves that particles, including the ones that make up us and everything around us, can be in multiple places at once.
That's the mind-blowing takeaway. Yeah, the experiment really is a powerful demonstration of how our everyday intuition about motion and reality completely falls apart in the quantum realm.
So if our classical understanding of the world is basically an illusion, what does this mean for our understanding of, well, everything?
That's a question that has been puzzling physicists and philosophers for decades.
Okay, I'm starting to see how this quantum stuff could make some people go a little crazy. If things aren't really in a definite place until we look at them, does that mean we're creating reality just by observing it?
Well, that's one interpretation of quantum mechanics. Yeah, it suggests that the observer isn't just passively watching the universe, they're actively participating in shaping it.
So, like if a tree falls in the forest and no one's around to hear it, doesn't make a sound. Except in this case, it's more like, does the tree even exist if no one sees it fall?
Yeah, it's a mind-bending concept, right? The double-slit experiment really throws a wrench into our traditional ideas of cause and effect. If particles don't follow definite paths until they're observed, what does that say about the nature of time or even free will?
Whoa, those are some deep questions.
Hmm.
Are you saying our choices might not even be real? That everything is predetermined?
Well, I wouldn't go that far. Quantum mechanics doesn't necessarily negate free will, but it does suggest that reality is much more fluid and uncertain than we might think. It opens up the possibility that there are multiple potential futures, and our choices influence which one becomes real.
So it's not all doom and gloom. There's still room for us to shape our own destiny.
Absolutely. I think quantum mechanics offers a really empowering message. It suggests that we're not just passive bystanders in a predetermined universe, but active participants in shaping reality.
That's a pretty optimistic take on a theory that's often portrayed as confusing and chaotic. So what does this all mean for me sitting here in my living room trying to wrap my head around all this quantum weirdness?
Well, maybe it means embracing the uncertainty, being open to the idea that there are things we don't know and may never know for sure. It challenges us to let go of our rigid classical view of the world and embrace the possibilities that quantum mechanics presents.
So instead of getting hung up on finding definitive answers, we should be celebrating the mystery and wonder of the quantum world.
Exactly. Quantum mechanics reminds us that the universe is full of surprises and that there's always more to discover. It's a call to stay curious, keep asking questions, and be open to new ways of understanding reality.
I don't know about you, but this whole deep dive has been a wild ride. We started by challenging our basic understanding of motion, dove into the mind-bending world of superposition and wave-particle duality, and ended up contemplating the nature of reality itself.
It's pretty amazing, isn't it, how a simple experiment with light and two slits can open up such profound questions about the universe and our place in it.
This deep dive has definitely given me a lot to think about, and maybe it's made me a little bit less certain about everything, which might not be such a bad thing after all.
Yeah, uncertainty can be a powerful catalyst for growth and discovery. It forces us to question assumptions, explore new ideas, and stay open to the wonders that the universe has to offer.
Well said. To all our listeners out there, if this deep dive into quantum mechanics has sparked your curiosity, I highly encourage you to check out the article we discussed today, The Illusion of a Single Path. It's a great starting point for exploring this fascinating and often mind-boggling field.
And remember, the journey of discovery doesn't end here. Keep exploring, keep questioning, and keep embracing the mystery.
That's a wrap on another thought-provoking deep dive. Until next time, keep those minds open and stay curious.